Duality theory, part 2, the dual. So here we'll look at the dual form of the constraint optimization problem. The dual function, theta d lambda mu. So this is the constraint optimization problem minimized with respect to x, the objective function f of x, subject to the inequality constraints g of x is less than equal to 0 and h of x is equal to 0. The Lagrangian is Lx lambda mu equals f of x plus lambda transpose g of x plus mu transpose h of x, and lambda is greater than equal to 0. The feasible set is script f, which is the set of all feasible points x that satisfy the inequality and the equality constraints. Therefore, for all I, g I x will be less than equal to 0, and for all j, hj of x will be equal to 0. The dual function is defined as follows. Theta d lambda mu equals infimum with respect to x of the Lagrangian Lx lambda mu. So what we are doing here is we are maximizing the Lagrangian with respect to x, and therefore we eliminate x. Therefore, theta d is only a function of lambda and mu. And since the Lagrangian is given by this expression, we have theta d lambda mu equals inf of f of x plus lambda transpose gx plus mu transpose hx, which is equal to infimum of f of x plus summation lambda I g I x plus summation mu j hj of x. And theta d being a function of lambda and mu, the dual variables, is a mapping from R L plus M to the real line. L is the cardinality of the set of all inequality constraints, and M is the cardinality of the set of all equality constraints. Therefore, lambda is a vector in RL and mu is a vector in Rm. Let's highlight this definition. Concavity of theta d lambda mu. Theorem 2, the dual function is concave. Hence, for any alpha between 0 and 1, theta d of a convex combination of lambda 1 and lambda 2, which is alpha lambda 1 plus 1 minus alpha lambda 2, is greater than equal to alpha times theta d lambda 1 plus 1 minus alpha theta d lambda 2. This is concavity with respect to lambda. And likewise, concavity with respect to mu is theta d of alpha mu 1 plus 1 minus alpha mu 2, which is a convex combination of mu 1 and mu 2, is greater than equal to alpha theta d of mu 1 plus 1 minus alpha theta d of mu 2. That's concavity with respect to mu. Now, you will see that I've color-coded all arguments when we revisit what a concave function is. So here I have a concave function, which is basically a cup facing upside down. The negative of a convex function is a concave function. And I have marked off 2 points, x1 and f of x1, x2 and f of x2. The red curve is the concave function. Let's take point alpha x1 plus 1 minus alpha x2, and this is that point here. This straight line segment is divided in the ratio alpha and 1 minus alpha. So this point here is alpha times f of x1 plus 1 minus alpha times f of x2, because this straight line segment is divided in the ratio alpha 1 minus alpha. And you can see the corresponding terms here. They are in green. Now, this is alpha x1 plus 1 minus alpha x2, and so this is f of alpha x1 plus 1 minus alpha x2. And what concavity means is that the function of a convex combination of 2 points is greater than equal to the convex combination of the functions of the 2 points. In other words, this curve should be above this straight line segment. That's concavity. And now we proceed to prove this theorem 2, which we now highlight. Okay. So let's prove concavity with respect to lambda. So I have 2 points, lambda 1 and lambda 2, and alpha lambda 1 plus 1 minus lambda 2 is a convex combination of the 2 points, lambda 1 and lambda 2. And I have to prove that theta d of the convex combination, which is alpha lambda 1 plus 1 minus alpha lambda 2, comma mu is greater than equal to alpha theta d lambda 1 mu plus 1 minus alpha times theta d lambda 2 comma mu. Proof. I begin with the left hand side, theta d lambda comma mu, where lambda is equal to the convex combination alpha lambda 1 plus 1 minus alpha lambda 2. This is equal to infimum of f of x plus mu transpose h of x plus lambda transpose g of x. What's inside the infimum, its argument, is the Lagrangian. And that's equal to infimum of f of x plus mu transpose g of x plus, I replace lambda with alpha lambda 1 plus 1 minus alpha 2. So what I have here is alpha lambda 1 plus 1 minus alpha lambda 2 transpose times g of x, which is equal to the following. What I have done here is I have broken up the f of x into 2 parts, an alpha part and a 1 minus alpha part. And I've done the same thing with the second term, mu transpose h of x. So I have here infimum with respect to x of alpha fx plus 1 minus alpha fx plus alpha mu transpose hx plus 1 minus alpha mu transpose hx. And the third term, I simply open up the parentheses. So I get plus alpha lambda 1 transpose g of x plus 1 minus alpha lambda 2 transpose g of x, which is equal to this. In this step, what I do is I lump all the alpha terms together, and separately I lump all the 1 minus alpha terms together. So I get this is equal to infimum of alpha fx plus alpha mu transpose hx plus alpha lambda 1 transpose g of x plus 1 minus alpha fx plus 1 minus alpha mu transpose hx plus 1 minus alpha lambda 2 transpose g of x. The next step is this is equal to infimum of alpha Lx lambda 1 mu plus 1 minus alpha Lx lambda 2 mu. And all I've done here is I've combined the alpha terms together and used the definition of the Lagrangian, and separately I've combined the 1 minus alpha terms together and again invoked the definition of the Lagrangian. And that's greater than equal to alpha times infimum of Lx lambda 1 mu plus 1 minus alpha infimum of Lx lambda 2 mu. Now this step warrants a little explanation. What I've done is I've taken the infimum over two arguments and then I've applied the infimum over each argument separately, which explains why I have the greater than equal to sign. That's because min of f plus g is always greater than equal to min of f plus min of g, which is equal to alpha theta d lambda 1 mu plus 1 minus alpha theta d lambda 2 mu, which is the right hand side of this inequality that I wanted to prove. I began with the left side and I ended up proving that the right side is greater than equal to, the left side is greater than equal to the right side. The last step is basically I'm invoking the definition of theta d, which is infimum over of the Lagrangian over x. And this completes our proof for concavity with respect to lambda. The next part of the proof is concavity with respect to mu. So I have to prove that theta d lambda comma alpha mu 1 plus 1 minus alpha mu 2 is greater than equal to alpha theta d lambda mu 1 plus 1 minus alpha theta d lambda mu 2. The proof for concavity of theta d lambda mu with respect to mu is along the same lines as that of concavity with respect to lambda and has been omitted. Another way to view is this. So each equality constraint can be viewed as two inequality constraints. H jx equals 0 is an equality constraint, and this can be viewed as a set of two inequality constraints. Hjx is less than equal to 0 and negative hjx is less than equal to 0. And therefore, the concavity with respect to lambda holds for concavity with respect to mu as well. Now let's look at the dual problem. Maximize theta d of lambda mu with respect to lambda and mu, of course. And the solution is lambda star mu star, which is arg sup of theta d lambda mu, the dual function. And since the dual function is infimum with respect to x of the Lagrangian, we get this expression for lambda star and mu star. And theta d star is the maximum value of the dual function theta d, which is by definition theta d lambda star mu star. So lambda star and mu star are where theta d acquires the maximum value. Compare this to the primal problem. This solution to the primal problem that minimizes the primal is x star. And look at the similarity. Here in the dual, you are maximizing with respect to lambda and mu. Here you are minimizing with respect to x. And in terms of the Lagrangian, in the dual problem, what you're doing is you first do the minimization with respect to x to eliminate the x, and then you do the maximization supremum. You do the reverse in the primal problem, where you first do the maximization with respect to the dual variables lambda and mu, and then you carry out the infimum. And this is theta p star, which is the minimum value of the primal problem, which is also the minimum value of the constraint optimization problem, the solution. And what we shall see now is that weak duality always holds. This is the condition where theta d star is always less than equal to theta p star. The maximum of the dual is always less than equal to the minimum of the primal. And under certain circumstances, the two are equal. So theta d star equals theta p star. That's what we shall be looking at next. Theorem 3, weak duality. The infimum of the dual is less than equal to the supremum of the primal, or theta d star is less than equal to theta p star. Proof. The infimum with respect to x of the Lagrangian is less than equal to the Lagrangian for any arbitrary value of x, obviously. Now we apply the supremum on both sides. So on the left side, we have supremum with respect to lambda greater than or equal to 0 mu of infimum with respect to x of the Lagrangian is less than equal to supremum of the Lagrangian. If the left side is less than equal to the right side, then the left side must be equal to the infimum of the right side. So we see that the left side is less than equal to infimum of the supremum of the Lagrangian. The left side is theta d star and the right side is theta p star. So we see that theta d star is less than equal to theta p star, which is the statement of the theorem. As a corollary to the previous theorem, we have the dual function is always less than or equal to the primal function. Theta d lambda mu is less than equal to theta p of x. Proof. We start with the theorem. So we just showed that theta d star is less than equal to theta p star, whence supremum of the infimum of the Lagrangian is less than equal to infimum of the supremum of the Lagrangian. Noting that there is a less than equal to sign here, we can remove the supremum from this side, whence we have inf of the Lagrangian is less than inf of the sup of the Lagrangian. Now again, because of this less than equal to sign here, we remove the inf from the right hand side, whence we have inf of the Lagrangian with respect to x is less than equal to sup of the Lagrangian with respect to lambda and mu. And this is the statement of the theorem, of this corollary. Duality gap is the difference theta p star minus theta d star. And since we learned that theta p star is always more than or equal to the theta d star, this duality gap is always greater than or equal to 0. Constraint qualification. These are used to establish sufficiency conditions for the duality gap to be 0, i.e. for strong duality to hold. So this is the duality gap, and theta p star is always more than or equal to theta d star. But when the two are equal, the duality gap becomes 0, and that's when theta p star equals theta d star. This is strong duality. Slater's condition. This is an example of a constraint qualification. The condition is that there exists a feasible point x0 in Rn such that all inequality constraints are strictly satisfied. Therefore, gi of x0 are all strictly less than 0. Hj of x0 is equal to 0 because x0 is a feasible point. Another way of looking at this is that the GIs are inactive constraints at x0. Now, we know that the equality constraints are always treated as active constraints. So they can never be strictly satisfied, but they are satisfied. Theorem 4, strong duality. If the objective function and all inequality constraint functions are convex, and all equality constraint functions are affine. By affine, we mean of the form A x equals B. The handwriting is not too good, but anyway. And Slater's condition is satisfied, then strong duality holds. So this theorem is a sufficient condition for strong duality. So the if part is this. The function f of x should be convex. All the inequality constraints should be convex. And the equality constraint should be affine. That is, it should be of the form ax minus b equals 0. And there must exist a point x0 such that gi of x0 is less than 0 and hj of x is equal to 0. So this is Slater's condition. And these three conditions on the top row define a convex constraint optimization problem. So if these conditions are satisfied, then theta p star equals theta d star, which is strong duality. So let's review the primal and the dual problems. In the primal problem, so what we have is theta p of x is the primal function, and that's the supremum with respect to the dual variables of the Lagrangian. So we are removing the dual variables from the Lagrangian by carrying out the supremum operator, and that gives us the primal function, which is a function of only the primal variable x. And the minimum of the primal function is at x star. This schematic shows theta p of x, the blue curve. And remember that in the infeasible region, theta p of x is infinite. So let's pretend that the left side and right side of this shaded region are infeasible. Then theta p of x would go to infinite on both sides. And it stays equal to the objective function in the feasible region. So this blue curve also represents part of the objective function. And this is the minimum of the primal function, theta p, and that's theta p star. So in other words, this point here will be x star. Dual. The dual function theta d lambda mu is the infimum of the Lagrangian with respect to the primal variable x. So we are removing the primal variable from x by taking the infimum with respect to it of the Lagrangian, and that gives us theta d, which is a function of only the dual variables. And the supremum or the maximum of the function theta d occurs at lambda star mu star. In this schematic, the dual function theta d is shown by this red curve. It's always concave, as we have seen. And just for simplicity, I've used this axis to represent both lambda and mu. And this is theta d star, where theta d lambda mu, the dual function, acquires its maximum value at theta d star. So this would be this point here. Let me use another color. This point here would be lambda star mu star. And duality gap says that theta p star is more than theta d star. Theta p of x is always above theta d of lambda mu. Now, why do we use the dual of a constraint optimization problem? There are several reasons for this. Sometimes it's algorithmically simpler to solve the dual, either because we have less number of constraints, so lambda and mu, the dimensionality of lambda and mu are together less than that of the dimensionality of x. So that makes it simpler to solve. Otherwise, you get simpler equations to solve the dual. And another thing is it's always concave, even if the objective function is not convex. So there's no guarantee that the theta p would be convex. Even if that's the case, theta d is concave. And so you can employ simpler algorithms to obtain theta d. And under certain circumstances, the duality gap is 0. When you hit the maximum of the dual, that's the saddle point, you automatically get the solution. And even if strong duality does not hold, it's always attractive to look at the dual, because it would tell you, if you're using the primal function, the duality gap will keep decreasing, and it'll tell you how close you are to the optimum of the primal. And of course, when strong duality holds, then we have a point called the saddle point, x star, lambda star, mu star. That's this point here.